text in the Western tradition by Anaximandros that talks about all things coming from the limitless and going back to the limitless. And in Greek, being without limit is the adjective for that is Ápeiron, so that explains the title of the talk. Okay, so but that's gonna be clear at the end of the talk. The way I want to get there is actually by putting to use a certain theory of vagueness that are developed in early works. We also talked very briefly about it during the first presentation of the conference by Professor Pudyakov. And I like to get that theory to interact with the problem of vagueness, which I haven't thought much about until recently, which is the problem of the many. And once I show to you how the theory of vagueness that I favor can solve the problem of the many, then that's going to give me the tools to be able to address the question of the lack of limits of ordinary objects. So let's see if I can move my slides. So more in detail, the structure of the talk is going to be the following. In the first section, I'm going to introduce you to the problem of the many, which is a particular problem that concerns the vagueness of ordinary objects. Then in the second section, very briefly, I want to argue that the problem of the many actually causes either to the unnoticed difficulties for many mainstream theories of vagueness. I'm just going to give you a very brief taste of that. In the third section, I'm going to move on to my own favorite theory, which I'm going to call the naive theory of vagueness. And after briefly presenting the main tenets of that theory, I'll show you how the theory, I think, can deal with the problem of the many in a very satisfactory way, which is not equal by the other mainstream theories. And in the final section, we're going to, having done this work, we're going to be in a position to spell out different senses in which ordinary objects can lack limits, and I'm going to argue for a particular way of understanding that. So that's the plan of the talk. Let me see. Sorry, I can't. Okay. So first thing, the problem of the many. Now let's fix on a very particular example for the rest of our talk. So take the Aegean Sea, and suppose you start from what's supposed to be the center of the sea, and you just go areas by areas, for example, westwards, so that finally you're out of the Aegean Sea and you're into the Ionian Sea, for example. And suppose that along this trajectory, you take very little areas one by one, and you go farther and farther away from the center of the Aegean Sea and closer to the Ionian Sea. So you can think of these areas of water as being very small, so say 1 square meter of area. But eventually, little by little, you're going to be able to leave the Aegean Sea and get to the Ionian. Now take an area that is more or less between the Aegean Sea and the Ionian, and call it area A. Now consider the following two objects. The first object that we can define is the Aegean plus A. And that's basically the object that has A as a part. Then forget about close to on the slides, it's not very important for our purposes, and otherwise coincides with Aegean. So A is in the middle, so it's not clear that it's a part of the Aegean, and it's not clear that it's not part of the Aegean. It's a borderline case of belonging to the Aegean, but by stipulation, this other object, the Aegean plus A, does have A as a part. So similarly, we can also define an object that is the Aegean minus A, and that's what you expect it's an object that does not have A as a part, then forget again about the second condition. And otherwise, has all the parts that the Aegean has. So we have the Aegean, A is a borderline part, and we have the Aegean plus A that has A as a part, and we have the Aegean minus A that doesn't have A as a part. Okay, now the question is, we consider that both the Aegean plus A and the Aegean minus A seem to have as good as claim to be a C as the Aegean has. They have the same properties that are relevant for being a C that the Aegean has. The Aegean obviously is a C, so if the Aegean plus A and the Aegean minus A have an equal right to be a C, they should also be a C. But certainly we have at least the difference between the Aegean plus A and the Aegean minus A. These are two different objects. One has A as a part, the other one doesn't. So if both are C's, then we get the result that there are at least two different C's in the region around the Aegean, which is absurd. There is only one C. Okay, so this is so basically what seemed to be a single C, the Aegean, splits up in at least two different objects, C's, that on the other end don't seem to be possibly located in roughly the same region. So that's the problem of the many. Of course, you can repeat it for small areas of water than A, and of course, the example of the Aegean is just an example. You take every ordinary object or every higher level scientific object, like a mass of liquid or a planet or whatever, or an organism, what have you. You're gonna, these objects are vague. They're gonna be parts, they are borderline parts. They're gonna be little objects that are borderline parts for them. And once you have borderline parts, you can use them the way we use A for the Aegean, and you're gonna be able to replicate the problem of the many for any such object. So generally, we're going to have every ordinary or higher level scientific object that seem to be unique is going to split into a myriad of different objects of the same kind. So for example, we take a planet, we take Mars, where we thought that we had only a single planet, Mars, we're going to have 1,000 and thousands of overlapping planets, which is an absurd result. So this is a very general problem, and it's been known in the philosophical literature as the problem of the many. It's been presented, I think, as far as I know, independently around the same time by two philosophers, Peter Unger and Peter Gitsch. Now I'm going to skip this slide. So obviously, it was clear already from the way I presented that the problem of the many has something essential to do with vagueness. We set up the problem by taking an object, the area A, which is a borderline part of the Aegean. So that's where vagueness enters into the picture. And we assume that a solution we assume I'm going to assume, at least, although there are some philosophers, for example, like David Lewis, that have embraced the opposite option. I'm going to assume that it's absurd to think that there is more than one sea in the region around the Aegean. So it's natural to expect that since the problem has to do with vagueness, it's natural to expect that the solution to the problem that explicates why at least one or two, the Aegean plus A or the Aegean minus A, is not a sea, that explanation should be derivable from a general theory of vagueness. So from a general vagueness, the main problems of vagueness are the Sorites paradox and borderline cases. So we expect that from a good theory of vagueness that explains the Sorites paradox and explains in what borderline cases consist, we expect from that theory that's also going to be able to explain to us why either the Aegean plus A is not a C or the Aegean minus A is not a C. So there's a general desideratum in the literature that the solution to the problem of the many should flow from a more general theory of vagueness. It shouldn't be an ad hoc solution just for the problem of the many. That should follow from our general solutions to an accounts of the Sorites paradox and of borderline cases and of vagueness more generally. So what I'd like to briefly argue, excuse me? Okay. Well, what I'd like to briefly argue now is actually that this methodological expectation is not met by many mainstream theories of vagueness. So these theories, I'm going to try to argue that these theories are not able to give a solution to the problem of the many simply on the basis of their solution to the Sorites paradox and to borderline cases. So this would, to argue this in full, would require going through every main theory of vagueness. Since my argumentative strategy is basically the same, structurally the same for all these theories, I'm just going to exemplify the strategy with one particular mainstream theory and leave for discussion if you're interested to see how the same strategy applies to other theories. So because it's particularly simple in many respects, I'm going to focus on epistemicism. So the idea there's really a sharp boundary between positive and negative cases of a vague predicate, and we just don't know where this boundary is. And more generally, borderline cases, according to epistemicism, are either positive or negative, and we're just ignorant about the answer to this question. Okay, so when we apply epistemicism to the situation of the problem of the many, in particular to the example of the Aegean, certainly it follows that the question of whether the Aegean is identical with the Aegean plus A or is identical with the Aegean minus A, that there's going to be a vague question. And according to epistemicism, one or the other is correct. So either the Aegean is identical with the Aegean plus A or the Aegean is identical with the Aegean minus A. So here we have a difference between the Aegean plus A and the Aegean minus A. It's only one of them that is identical with the Aegean. We just don't know which. That's unknowable, but it's a fact. It's simply an unknowable fact. So that's epistemicism applied to the Aegean and to the Aegean plus A and the Aegean minus A, and that gives us a way to discriminate between the two with respect to the question which of the two is the Aegean. But notice that this doesn't give us a way to discriminate between the two in terms of the question of which of the two is a C. Because the epistemicism only tells us that it's only one of the two that is identical to the Aegean, but doesn't seem to have the resources to account for the fact that only one of the two is the C. In fact, since both the Aegean plus A and the Aegean minus A, both of them have all the properties that seem to be relevant to be a C, also according to epistemicism, also including the property that have to do with vagueness, and therefore epistemicism are important for vague objects. So the prominent example here of a property that epistemicism thinks is important for vague objects is the property of having unknowable parts. According to epistemicism, vague objects have borderline parts, and what it means for these parts to be borderline, it means that they're either unknowably part of the objects or unknowably not part of the objects. But that doesn't differentiate between the Aegean plus A and the Aegean minus A. For example, if you think back about the example, I said take a trajectory from the Aegean to the Ionian, and then just take A to be an area in the middle of that trajectory. Then suppose you take a similar area of water just a bit closer to the union, call that A prime, so like the successor of A on that trajectory. And then take an area of water that is just a little bit closer to the Aegean than A, and call that prime A, so like the predecessor of A. Then it can still be, on epistemicism, it's still the case, the A prime, the successor of A, can be an unknowable part of the Aegean plus A, so the Aegean plus A still has unknowable parts, and conversely, the predecessor of A could still be an unknowable part of the Aegean minus A. So also the Aegean minus A can have unknowable parts. So there's no way, as far as epistemicism is concerned, to discriminate one of the two, either the Aegean plus A or the Aegean minus A, as lacking properties that are important for being a C. They have all properties that are important for being a C. Okay, so epistemicism might, in some, epistemicism might well give a solution to the question which of the two between the Aegean plus A and the Aegean minus A is identical with the Aegean, but doesn't have a good account of which of the two of these objects is a C. As far as epistemicism is concerned, both still have equal rights to be counted as being a C. So we are not really, we don't have the resources to address the problem of the many if we stick to epistemicism. So that's the point, and I think once you see the structure of this point, you can see they can be replicated from many different theories of vagueness. For example, we can say basically everything I just said concerning, sorry, I'm having some trouble in moving the slides every now and then. But basically, if you take supervaluationism, you can say everything I said about epistemicism, simply substituting the property of having unknowable parts with a property of having indefinite parts. And the same argument goes through. Now okay. So that's the stuff about supervaluationism. Okay, so that ends my my criticism of mainstream theories. I mean, this is the general argumentative strategy. It can be applied to many mainstream theories of vagueness. Now, I'm more interested in rather than criticizing other theories. I'm more interested in developing further the theory of vagueness that I proposed in earlier work. So I'm going to briefly introduce you to the general form of the theory, and then I'll show it to you how the theory can be applied to solve in an interesting new way the problem of the many. So basically, this is an important part of the theory, of course, is the formal system. And the formal system, I call it on the slides NLS. And this is basically the best way of thinking about that is to think of it really as a non-logical theory with a certain axiom, which we're going to call theory N for naive, plus a background non-classical logic, which we're going to call LS. And just as a spoiler, we're going to call it like this because the main feature of this non-classical logic is that it lacks the property of transitivity. So like in Gentzen style presentation, there would be the property of cut, which is Schnitt in German. So that's why you have LS, or lack of Schnitt, lack of transitivity. Okay, so these are the two main components of the formal theory, the theory and the background logic. So let me first present you with a theory, which is very simple. I call it the naive theory of vagueness, and that's basically a single, for our purposes, we can take it to be a single sentence, but it really has three main elements. So focusing on a case of vagueness, for example, vagueness in being in parthood. Take the predicate P of xy to mean the y is a part of x. And then let I, for example, be the Ionian. Then take now take again a trajectory from the Ionian, this time just to keep the example different, from the Ionian to the Adriatic, divided in small areas, from the center of the Ionian to the center of the Adriatic. And suppose in 1 million step, we get in 1 million areas, we manage to get from the Ionian to the Adriatic, and just number these areas accordingly. So 0 is an area in the center of the Ionian, and 1 million is an area at the center of the Adriatic. Okay, and finally, S is simply a predicate for C's. So under this assumption, we can state the naive theory of vagueness. As I said, is this three-argument conjunction. The first conjunct says that 0 is a part of the Ionian. 0, remember, is an area at the center of the Ionian. The second conjunct says that 1 million is not part of the Ionian. Remember, 1 million is an area that is at the center of the Adriatic. And up to now, these are simply platitudes. Almost everyone would believe them. The real punch of the theory comes with the third conjunct, a famous principle of tolerance that says that for every x there is a C, and for every y there's a little area. Then y is a part of x if and only if the successor of y along a fixed trajectory is also part of x. So basically it says that if an area is part of a C, then an area that is just a little bit farther away from the center of the C is still part of the same C. Okay, that's a famous principle of tolerance. And of course, in classical logic, if we accept this principle, it would lead to the Socrates paradox, because we, using the fact that 0 is part of the Ionian, then we can argue that 1 is part of the Ionian, that 2 is part of the Ionian, that 3 is a part of the Ionian, until we arrive in classical logic in a valid way to the absurd conclusion that also 1 million is part of the Ionian. So that's why if we want to have this theory, then we should reject classical logic, and we should adopt a different non-classical logic. So then we come to the background logic, LS, the non-transitive logic, and this is a bit more complicated to introduce. Let me try to do my best. Also, it'd be clearer if I was able to be there in person, but I try to do it on the slides in a intelligible way. So the easiest way to think about LS is to think about it semantically as defined over a certain class of model. So what is a model for LS? So it's basically a 7-tuple where we have several elements. First element is simply a universe of discourse. The second element, important one, second and third elements, is basically a set of values for the interpretation of all the formulae, ordered by a partial order. Sorry, I got the wrong slide. Let me go. Now here you have a complex definition of the values and the order of them. Here is, I think, a much easier depiction using a HSE diagram. And this is basically the set of values with a partial order. So they form the lattice that you see, and then I put the numbers just so that you can understand the order of the lattice in terms of subset inclusion. But this is basically the space of values that we have in the logic, and as always, the top value is the top values are the good values, and the bottom values are the bad values. I'll be more specific about good and bad values shortly. But this is our value space. Okay, on this value space, we can distinguish, we're going to distinguish 3 different types of values. So we're going to have very good values And these are the three values that you see indicated on the same structure with a double circle. So it's those three values. Then we're going to have a kind of values that are still good values, but are not very good values. And these are the values, these are the four values that you see designated with a simple circle. So I call the very good values, we're going to call them the designated values. And the good but not very good values, we can call them the tolerated values. Then finally, we also, the remaining three values, those that are designated with a square, these are the bad values, the one that real model falsity. So our lattice is divided in, the elements of our lattice are divided exhaustively into these three sets of values: designated values, tolerated values, and values that are neither designated nor tolerated, the bad values. Now, since we already have go back one slide, since we already have this ordering on the lattice, that's already going to give us automatically the interpretation for conjunction universal quantification just by taking the greatest lower bound and conversely the interpretation for disjunction, in particular quantification by taking the least upper bound. So a lot of the interpretation is already done simply by the lattice order. What we still need to add to our model for the interpretation is a function with which to interpret negation in the language. And that's the function that you have on this slide. So basically the dotted lines that connect two elements of the lattice, this is supposed to represent the function with which we are going to interpret negation. So the items connected, the values connected by the dotted line, you have to think of them as one being the negation of the other. So as you see, negation is going to basically flip symmetrically the values in our lattice from left to right and right to left. Okay, so that's all we need in terms of the structure of the lattice. And as always, we're going to have an interpretation function that's going to project atomic formulae of certain arity I and ipoles on to a particular value in the model. And then, as I already mentioned, once we have this interpretation of atomic formula, we can extend in a very usual way the interpretation to a full evaluation for arbitrary formulae in the language using greatest lower bound for conjunction and universal quantification, least upper bound for disjunction and particular quantification, and the particular negation function I show you in the previous slides to interpret negation. So now we're going to have, we already have an interpretation, given a model, an interpretation for all the formulae of the language. And now if you want, the crucial trick of the construction is when, once we have all these models, is how we define the relation of logical consequence from a certain set of premises gamma to a set of premises, to a set of conclusions delta. So we say that we have a logical consequence from gamma to delta if and only if for every LS model, and I'm going to forget about the complication with assignments, basically if every premise gets a value that is designated in the model, remember the very good values, then at least some of the conclusion must get not a designated value, that will be too demanding. We only require that at least one of the conclusion gets an at least tolerated value, either tolerated or designated. So this way we allow for a drop of quality of value from the premises to the conclusion. An argument can be valid, the premises have a designated value and the conclusion only have a tolerated value. And this is this drop that we are allowing from designated to tolerated that then, of course, by iterating it, is going to cause failure of transitivity. So that's basically at the level of this definition of logical consequence from designated to tolerated values that we are really generating the possibility of failure of transitivity. And that's what I just said. In fact, transitivity is going to fail in a very extreme way, even for argument with just one premise and just one conclusion. The principle that if phi entails psi, and psi entails chi, then phi entails chi, this very simple principle of transitivity is going to fail. And we can see it with an example applied to the naive theory of vagueness we described earlier. So if we let now, for brevity, pi of n be an abbreviation of n is part of the Ionian, then you can see that if we take the relation of logical consequence and we relativize it to the naive theory, so this conjunction that I gave you earlier on, so we always assume that that's a premise, that that's an implicit premise, then we're going to get that the resulting system, NLS, is going to prove from the empty set, is going to derive pi 1, and then from pi 1, the system entails pi 2. Transitivity would then require that from the empty set, the system entails pi 2, but that fails. Because pi 1 can get a tolerated value, and then pi 2 can get a value that is neither designated nor tolerated. So that's why even this simple form of transitivity fails, and it does fail exactly, for example, using the naive theory of vagueness, and that's how the naive theory of vagueness is going to block, for example, the Sorites paradox. So if you analyze the Sorites paradox, you're going to see that you're going to need transitivity to reach the absurd conclusion, but now we've shown that transitivity fails exactly when you're trying to do that type of reasoning. So NLS it's an interesting system. It's in a sense it's very powerful. It's weak enough so that it makes the principle of tolerance consistent, but strong enough so that it has what I call a complementative negation. So by this I mean a negation that obeys both the law of excluded middle and the law of non-contradiction, as the full deduction theorem for the conditional defined in the standard way. So you have both a generalized version of modus ponens and a generalized version of a conditional proof. That's what I mean. And as a fully extensional theories of conjunction, disjunction, and quantification, where by fully extensional I mean that the truth, for example, for conjunction, that the truth of the two conjuncts is necessary and sufficient for the truth of the conjunction, and similarly for disjunction and quantification. And I think this combination of features, as far as I know, is rather unique among systems of vagueness. So I think it's at least an interesting system that's a good competitor in the debate among theories of vagueness. All right. So let's. So this is work I've done in the past. Now I would like to apply this framework to the problem of the many, because it's something that I've never done before. And it's one of the main contributions of this work, of this paper. Now on the naive theory of vagueness, I was already talking earlier about properties of C's that have to do with vagueness. On the naive theory of vagueness, a property of C's that is important, a property that is important for C's and is related to vagueness is the property of lacking sharp boundaries. If you like the naive theory of vagueness, then you should think the C's lack sharp boundaries in the tolerance sense. If an area is part of a C, then also the immediately following area of water is also part of the C. So if you think the Cs have this property, then actually we can rule out that both the Gn plus A and the Gn minus A have equal rights to be a C, which is what's desired from a solution to the problem of the many. So let me briefly show to you how we can do that, with a very informal reasoning that could be formalized in a naive theory, but I think the informal version is going to be enough. So by the law of excluded middle, A is either part of the Gn or is not. Now, let's consider these two possibilities in turn. If A is part of the Gn, then take the predecessor of A. Then the predecessor of A is gonna be part of the Gn minus A, but A, which is its successor, is not gonna be part of the Gn minus A. So the Gn minus A is gonna have a sharp boundary after the predecessor of A. The predecessor of A is gonna be part of it, but immediately following area of water, A is not gonna be a part of the Gn minus A. So the Gn minus A is gonna have a sharp boundary, and that disqualifies the Gn minus A for being a C, because he has a sharp boundary, and Cs don't have sharp boundaries. Okay, so if A is part of the Gn, then the Gn minus A is not a good candidate for being a C, so we can rule it out. Conversely, for the other possibility, if A is not part of the Gn, then we take the Gn plus A this time, and we have the A is part of the Gn plus A, but the successor of A is not part of the Gn plus A, in which case now is the Gn plus A, there's a sharp boundary, because A is part of it, but the successor of A is not part of it. So in this case, the Gn plus A has a sharp boundary, and that disqualifies it for being a C. So either A is part of the Gn or A is not part of the Gn by excluded middle. And in other case, we have seen that at least one of the two candidates, the Gn minus A in the first case and the Gn plus A in the second case, is not, after all, a good candidate for being a C. So in other case, we only have one candidate for being a C. So in this sense, we can show with a naive theory of vagueness that there is only exactly one and only one C in the region around the Aegean, which is what was required to solve the problem of the many. Now, this is the informal reasoning. If you formalize it, I like to make this note. If you formalize it, you're going to see that the reasoning is not formally valid in LS because it uses a form of reasoning by cases that is not formally valid. But because in both hypotheses, we didn't use the principle, and we didn't use an application or the principle of tolerance. One can argue that although the reasoning is not formally valid in the system, is still truth-preserving in a system. So if you want to put it like that, you can say that the reasoning is materially valid. So it's a safe reasoning once one understands the right models of the system, but it's not unrestrictedly valid as an argument form. So that's an important note that I wanted to make. All right. And of course, just as the problem of the many was a general problem, also this solution extends generally to every ordinary object. Okay. So much for what I wanted to say concerning the application of the naive theory to the problem of the many. I'd like to use the last minutes of the presentation to show to you how this theory can then be used to investigate several notions in an interesting way, several notions of infinity as applied to ordinary objects. Now, first, some definition. For set, say that a set X is unbounded. If we have an injective function F, there's a certain domain that includes the set and a codomain that is included in the domain. and is such that at least one member of the set is not an element, doesn't belong to the codomain of the function, and the function is such that basically, if it's applied to a member of the set, keeps us within the set. Now this is this notion of being unbounded. This is I've just defined it for sets, but we can apply it also to objects if we introduce further notions. So say that a decomposition of a material object is isomeric if it basically decomposes the relevant objects in parts that are equal in shape and in a positive size. Obviously, very exactly parts of the same type. And if we have a set theoretic property that is related to infinity, then we can say that the property applies to an object if there is an isomeric decomposition with respect to which the set of the parts of the object has the set theoretic property. So in particular, if we do this with the notion of unboundedness, then on the naive theory of vagueness, we get the result that vague objects, because they lack sharp boundaries, they're going to be unbounded, because there is if we take an isomeric decomposition of the object that is small enough, for example, in the case of the Aegean, we decompose the Aegean in small enough areas, then because we have the principle of tolerance, that's going to give us the function that always keeps us within the Aegean, but on the other hand, as elements outside of the Aegean. So the set of areas is going to be unbounded, and so by this transmission of the property, also the Aegean itself is unbounded. Now, of course, the property of being unbounded is probably equivalent to a very familiar property in set theory, which is the property of being usually called a Dedekind infinite. That just means a set is Dedekind infinite if there is an injection from it to a proper subset of it. And of course, it's very easy to see these two proper, the Dedekind infinity and unboundedness are equivalent. So since on the naive theory of vagueness, vague objects are unbounded, it follows that vague objects are also Dedekind infinite. So for example, the Aegean is Dedekind infinite on the naive theory of vagueness. Of course, there's also another notion of vagueness under which an object like the Aegean is not infinite, right? Because it doesn't spread infinitely in any direction. So this is the idea of infinity, according to which an infinite set never ends. It goes on forever. So let's spell it out more precisely. We can say that set X is never ending. Again, if there is an injective function F, as before, as a domain that includes the set and a codomain included in the domain, such that, again, some member of the set is not in the codomain of the function, which together with injectivity basically tells you that there is at least, in the graph of the function, there's at least one line of the graph that goes on, that doesn't go in circle, goes on in a straight line. And then for every element, this time the second condition changes. Now for every element of the domain, the function applied to it keeps us within the set. And of course, in this sense, there is no vague objects, even on the naive theory of vagueness, are not never-ending, because they don't spread infinitely into any direction. Now, of course, similar to what we have before, there's a very well-known property in set theory, which is the standard property of infinity, Cantor infinity, which basically means there is an injection from the natural numbers to the set. That at least on countable domains, is equivalent with the property of never-endingness they have just defined. Now, this might seem puzzling because in classical mathematics, we also know the Cantor infinity is equivalent with Dedekind infinity. So since I want to say that vague objects are Dedekind infinite but not Cantor infinite, this might be puzzling. But it's not. But that's what we have in a naive theory. In the naive theory, we can prove that vague objects are Dedekind infinite, but we can prove that they are not Cantor infinite. And the usual argument, like the typical argument that in classical mathematics goes from Dedekind infinity to Cantor infinity is simply an argument by induction. And once you have induction on the natural numbers, and once you have the naive theory of vagueness, it's one can show that induction. It's easy to show that induction on natural numbers is no longer a valid principle. Sorry. All right. So that's what I was saying. Take if you fix on a suitable isomeric decomposition, then we can show in the naive theory of vagueness that the number of parts, for example, of the Aegean is going to be different from any standard natural number. You cannot say that the Aegean has 1 million parts, because if it has 1 million parts, then by tolerance, it would have 1,000,001 parts. So it would be an inconsistent claim. So we can show that there is no standard natural number. There is the number of parts of the Aegean. But of course, the number of parts of the Aegean is limited. It's not going to have one Google parts. So it's going to be not only is going to be finite, it's going to have a finite upper end. So we're going to have finite natural numbers that are non-standard, and that's why induction on natural numbers fails on the naive theory. In fact, we're going to have many non-standard natural numbers because, for example, we're going to distinguish between the size of the Aegean from the size of the parts of the Atlantic. The parts of the Atlantic are going to be more than the parts of the Aegean, and both are going to be non-standard natural numbers. Now, of course, there's another, when we apply, when we try to see in what sense natural objects lack limits. From ancient philosophy, we are very well acquainted with the idea that they are infinitely, at least potentially, infinitely divisible. And that there was the standard way in which traditionally the ordinary objects have been thought to lack limits because they are infinitely divisible. But that's not a very as far as I'm concerned, that's not a very interesting sense in which not ordinary objects lack a limit. Of course, if you have potential infinite divisibility, then of course there is an infinite number of divisions you can make, or an infinite number of parts that these objects, at least in principle, have. So that's fine, but that doesn't really show in a more physical sense that these objects lack a limit. The limit of an object should be something like a line on one side of which the object is only occupied by the object, and the other side of the line is only unoccupied by the object. But it's easy to see that for natural the phenomenon of infinite divisibility doesn't give us that ordinary objects don't have a limit in that sense. I mean, they would take the example of a road, and suppose you start taking its half, then from the other half you take half of it, from the remaining quarter you take half of it, and so on. So you get closer and closer to the whole road by taking always half of the part of what you were taking before. Does the road have a limit in that direction? Well, it will lack a limit if the corresponding progression had no least upper bound. But of course, the corresponding progression does have a least upper bound. It's just one, even in the rational number. So it's not using the phenomenon of infinite divisibility. We don't really get a physical sense in which an ordinary object doesn't have a limit. In fact, we get quite the opposite, right? Because if we take the constitutive parts of the road, or the half, then the quarter, and then the eighth, the 16th, and so on, these parts never reach actually what is the effective limit of the object. So that's the grain of truth, if you want, in the first paradox of Zeno, the dichotomy, that we never reach this way the limit of the object, but the limit is there, is the limit of the object. Whereas with the notion of unboundedness that I developed earlier, I think that gives us a much better sense in which an ordinary object is without limit, because if we take any part that is supposed to be the limit, then by the principle of tolerance, we can always add to the object a part that is even farther away from the object, and we're going to remain within the object. So I suggest that contrary to come back to the original topic of a talk, that contrary to ancient Greek thought, the fullest manifestation of the lack of limits for ordinary objects is not when we divide them into smaller and smaller parts, the infinite divisibility question, but it's when we consider how far they extend in a certain direction, and that's what's given us by vagueness, and in particular by the naive theory of vagueness. I think that's a much richer sense in which ordinary objects can be said to lack limit, although in the other sense, in the Cantor sense, we've seen that they're certainly finite objects. That's all I wanted to say. Thanks a lot for your attention. And here I give you some references.
Yeah, thank you very much. Yeah.